A square box beam is constructed from 4 planks as shown. Knowing that the spacing between the nails is 1.75 inches and the beam is subjected to a vertical shear of magnitude 600 pounds, determine the shearing force in each nail. So a couple things just conceptually looking at this. We got to remember we're going to be using our shear flow on here. And remember that shear flow is a shear stress per unit length. That's why the 1.75 inches is important, because we're going to calculate out the shear flow, multiply it by that length to find out the shear force. As we also look at it, we can see that I'm just highlighting here, these are our 4 boards. You can see this is all put together symmetrically. So the force should be the same in all of these, because no matter how we calculate it, it's all going to work out to be the same. And so how do we go about solving this? Well, we've got 2 big things that we're going to sit there and look at. And my, So we're going to determine the shear force per unit length along each edge of the upper plank. We're only going to do the upper because the upper and lower are going to be the exact same because of symmetry. And then after that, based on that space in between the nails, we're going to find the shear force in each nail. So as we look at it, we're developing a vertical force of 600 pounds. It's positive, so we're assuming it's down. But since everything's symmetrical, even if it's going up, it's not going to matter. So that means for my shear flow, I'm going to start here, and things are going to flow till we get back here. Why is that important? It's important for calculating out Q and knowing which area is going to be driving the force. Because if I look at it here, let's mark it in red, this is where the nail is going to be experiencing shear force. And also right here. So as I'm calculating out the shear flow, it's going to be based around basically this piece of wood, because that's where the shear starts to flow. That's what's going to be pushing everything. So that's what all our Q is going to be based on. So now that conceptually we've got everything there, let's actually start looking at solving the problem. So I have my box beam sitting here, and so what we need to do is we need to determine that shear force per unit length. And for the upper plank, what we're going to have to do is we're going to have to calculate out Q. So what's our Q again? Q is really what's driving that shear force itself. So Q is equal to Y prime bar times A prime. So as I'm looking at it, I have this 3-inch box here. And it is a symmetrical box, so it's 3 inches across here. But since it's all symmetrical, I know that if I take this as my 0 point, from here to the bottom of my beam, it's going to be what? It's going to be 1.5 inches. I know that because the inside of this is 3 inches. So what's my area for Q? It's this guy right here. That is my transformed area. That's what's driving everything. So I need to know what my Y bar prime is. So I'm looking at where the centroid of that guy is. That guy's going to be in the middle of the beam. I need to know how thick the beam is. Well, I have a 3-inch area in the middle. On the outside, it's 4.5 inches. So that leaves me 1.5 inches of space. So that means that this has to be. These boards are all 3/4 of an inch thick. So 3/4 of an inch, half of that is going to be 375. 375 plus 1.5 will give us what the distance to that centroid of that section is, which is going to be 1.875, which you might have noticed is already listed over here. So that is how we find our Y bar prime, 1.875 inches. And so the area, it's just the transform area, so we're looking at this area here, 3 inches times 3/4 of an inch. Okay, so if I multiply all that together, I have a Q, and this is my transformed area, what's pushing on everything, 4.22 cubic inches. Okay, so now that I've got that, how do I calculate out my shear flow? Well, my shear flow, Q, is going to be V big Q divided by I. Okay, and that's going to give us the force per unit length. Well, I am going to need now, what is my I? So the overall beam cross-section, it's a rectangle, so I know that I is going to be base height cubed over 12. Now, this is a hollow box. What am I going to do? I have to use superposition. To get the hollow box, I'm going to take the rectangle, subtract the rectangle out of the middle. So the overall rectangle is 4.5 inches. Now it's a 4.5 inches on side, so it's going to be 4.5 inches times 4.5 inches cubed, or just 4.5 inches to the fourth divided by 12. I'm going to subtract from that the inside, which is 3 inches on side. So it'll be 3 times 3 inches cubed divided by 12, or just 3 inches to the fourth divided by 12. And then if I multiply that together, I get I of 27.42 inches to the fourth. Now I have my information. I can plug it in and find out what my shear flow is. So my shear flow V is 600 pounds. Q, 4.22 cubic inches, divided by I, 27.42 inches to the fourth. So that will give me a total shear flow of 92.3 pounds per inch. Now, since I want to know what's in each fastener, the thing is that 93.2 pounds, we have two different, here and here. So that's over both edges. That's not just one edge. So if I want to take it and just make it one edge, and we'll call it lowercase f just to get the edge force, the smaller force on its own, well, that's going to have to be Q divided by 2, because we have this entire shear force is over 2 areas. And so once I do that, I get 46.15 pounds per inch on each edge. So it's on the edge. Okay, so now I want to find the force. And so what we have here is a force per length. Well, now I know what my length is. It's 1.75 inches. That's the distance between my nails. So to find the full force, I'm going to take my force per unit length, and I'm going to multiply it by the length that I have. So 46.15 pounds per inch multiplied by that 1.75 inches that we have in our problem, because that's how our nails are spaced. And so that'll give us a force in each nail of 80.8 pounds. And so now that we have this force, what we could do is, okay, well, say the nail is 1/8 of an inch in diameter, you know what material the nail's made of, you can calculate out the stress in the nail based on the force that's being applied from the box load. And who knows, maybe the nails are fine. Maybe you can move them farther apart, use less nails and save money. You know, what would the force be if I had these guys at 2 inches apart? So what would we do is you just go back and take that 46.15 and multiply by 2. And what do you end up getting? Actually, you end up getting 92.3 pounds of force. Well, let's say, what if the nails are 4 inches apart? You just take that 46.15, multiply it by 4, and now it's all of a sudden you've got 184.6 pounds of force in each nail. So this is really something, once you get the base equation set up, you can start playing with spacing of your fasteners to minimize the amount of fasteners you want to use. Because you can sit there and calculate out what my stress in the fastener itself is, assuming whatever factor of safety that you want to use, and you can minimize the nails. Yeah, you can put these nails every 1/4 of an inch, and it'll see less force and everything. But a lot of times you're trying to figure out what's the most economical way to do things, and obviously the most economical way to do things would be use the least amount of fasteners. But you want to still do that and be safe, and so that's why I use a factor safety on the shear stress in the fastener. And you can start to see where all of the stuff that we've talked about in the entire class, it all starts to piece together, and we can use different little things like this to figure out those stresses that we talked about way in the beginning of the class.